Welcome to the deep dive. Ever looked at, say, two sets of data and wondered which one really varies more, especially if they're measured totally differently?
Uh-huh. It's a common problem.
Well, today we're diving into a neat tool for that, relative dispersion, and specifically the coefficient of variation, or CV.
Exactly. We often use standard deviation for spread, right?
Yeah.
But the CV, it kind of adjusts for scale. It lets us compare variability in a proportional way.
So even if the averages are way off or the units don't match?
Precisely. Think about comparing investment returns, like the consistency of a small startup versus a huge established company. The CV can really help there.
Okay, interesting. So let's break it down. What exactly is this coefficient of variation? What's the formula look like?
So, simply put, the CV tells you how much variability there is relative to the average or the mean of your data.
Relative to mean.
And the formula is pretty straightforward.
Yeah.
It's just the standard deviation divided by the mean. SD over mean.
Standard deviation divided by mean.
Okay.
Got it.
Yeah, so the standard deviation gives you that absolute spread, how much the numbers bounce around. But dividing by the mean, that scales the bounce relative to the central value.
Right. So why not just use standard deviation all the time? When does the CV, really become more useful?
Well, imagine comparing stock price volatility, say a $10 stock and a $100 stock.
Okay.
A $5 swing, a $5 standard deviation,
Yeah.
feels huge for the $10 stock, right? That's 50% of its price.
Yeah, definitely.
But for the $100 stock, a $5 swing is only 5%. Less dramatic, relatively speaking. The CV captures that difference because it factors in the average price. It puts them on a level playing field for comparison.
Makes sense. It's all about the context, the relative scale. Okay, now you mentioned the formula involves dividing by the mean. What if the mean is 0?
That's a really important point. If the mean is 0, the CD is undefined.
Because you can't divide by 0.
Exactly. Mathematically impossible, and conceptually, well, relative variability doesn't make much sense if your central point is 0. There's no baseline magnitude to compare the variation against, really.
Gotcha. Division by 0 is out. So going back to comparing different things, maybe weights in kilograms versus lengths in miles, how does CV handle that?
That's one of its neatest tricks. Because CV is a ratio standard deviation divided by the mean, the units actually cancel out.
Oh, okay.
So standard deviation is in, say, kilograms, and the mean is in kilograms. Kilograms over kilograms. They cancel. You end up with a pure number, a unitless measure.
So you could genuinely compare the relative consistency of weights in kilos versus, I don't know, temperatures in Celsius.
You absolutely could. It tells you the relative spread, regardless of the original units. Very useful.
That does sound powerful. Now, can the CV value ever be negative?
Generally, no.
Okay.
Think about the formula. Standard deviation mean. Standard deviation, by definition, measures spread, so it can't be negative. It's always 0 or positive.
Right.
And usually when we're calculating CV in practical situations, the mean is positive. So you're dividing a non-negative number by a positive number, the result, non-negative.
Okay, so usually positive or 0. Are there times when the CV might be, I don't know, a bit misleading? When should we be careful?
Yeah, there are limitations.
Yeah.
If your data is heavily skewed, lopsided,
Mhm.
the mean might not be a great measure of the center anymore. And if the mean isn't representative, then the CV, which relies on the mean, might be less reliable too.
Okay, skewed data is one thing. Anything else?
Outliers. Extreme values can pull both the standard deviation and the mean way off.
Ah, right. They distort the picture.
Exactly. So if you have significant outliers, they can definitely skew your CV value, making things look more or less variable than they perhaps really are in a typical sense.
Good to keep in mind, I also read it's used a lot in finance for risk.
Oh, absolutely. In finance, it's super useful. Investors often use the CV to compare the risk-adjusted return of different investments.
How does that work?
Well, they typically calculate it as the standard deviation of the investment's returns, the measure of risk or volatility divided by the average return. So a lower CV means you're getting less volatility, less risk for every unit of expected return. It helps compare investments that might have very different average returns and volatility levels.
That's a clever way to standardize risk comparison. One last thing, is there a difference in calculating CV for just a sample of data versus the whole population?
The basic idea, the concept of relative variability, stays exactly the same.
Okay.
But the specific formula for standard deviation is slightly different when you're calculating it from a sample versus the whole population. You use N1 in the denominator for the sample variance, remember?
Right, the sample correction.
Yeah. So that slightly different standard deviation value means the sample CV will be slightly different from the population CV. But the interpretation,
Yeah.
still about relative spread.
Okay, great. So boiling it down, the big takeaway seems to be that the coefficient of variation gives us this standardized measure of spread relative to the average. Super helpful for comparing data sets with different means or even different units.
That's the core of it, yes. It adds that layer of relative context that standard deviation alone doesn't always provide.
So for you listening, maybe think about where you encounter data comparisons. Could the coefficient of variation offer a new perspective? What seemingly unrelated things could you now compare on, well, a more level playing field using this idea of relative variation? Something to chew on. Thanks for tuning in to the deep dive.
Catch you next time.